What I want to share in this video today is an amazing Olympiad math problem, actually my favorite problem that I've ever encountered in my life. Now, what it's asking us is find the sum of the of 98 terms of the 100 terms in the sequence with n starting at 2 of 1 over log base n of 100 factorial. Now, what does this even mean? This looks incredibly intimidating. First of all, it combines three terrifying concepts: one of sequences and series and their sums, more likely, logarithms, and factorials. Worse yet, this problem contains 100 factorial. Now, to think about how big 100 factorial is, it's unimaginably large. Humans cannot even think of how large it is in terms of quantifiable objects. For example, 100 factorial is approximately, if you look at it on the calculator, 9.3 times 10 to the 157th. That is extremely big, and that's extremely bigger than 10 to the 100, which is Google, what we call Google. Now, just to put things in perspective, the age of our universe is 1.37 times 10 to the 10th power. So right away, Google is way larger than that. So that means that the age of our universe to the power of 10 doesn't even scratch the surface of what it means to hit 100 factorial. That's how big it is. Now, I know I'm intimidating you a lot by presenting this sheer size of 100 factorial, but you might realize that any math problem, especially an Olympiad math problem, requires clever problem solving to find a good solution. And this is exactly why this is my favorite problem. It combines three incredibly scary looking things: sigma notation, sums, logarithms, and factorials. And you only need two properties, mathematical properties, to solve this equation, and problem, and it becomes super easy after that. So let's look at this. What is it actually saying? It's asking us to find the sum of 98 terms starting at n equals 2. So let's write them out a bit more. So we have 1 over log base 2 of 100 factorial plus 1 over log base 3 of 100 factorial plus ... and the ... just means that we know the pattern from here on, or we hope that people will understand it. In that case, it'll be 1 over log base 4 of 100 factorial plus 1 over log base 5 of 100 factorial plus 1 over log base 6 of 100 factorial. You get it. So on and so forth, all the way until we get to the last term, which is 100. And that's 1 over log base 100 of 100 factorial. All right. This doesn't really seem to help too much, does it? But we'll show you how helpful this can be. First of all, this is a good time to introduce one important property. Property number 1, involving logarithms. And you only need two properties of logarithms. The first states this: log base c, and I'm just gonna use I'm gonna color code this, so I'm gonna just pre-write the colors like this. So you get this expression here: log base b, actually the base b of result a is equal to 1 over log base a with result b. And I call it result because log base b of a is the power to which you raise b to get a, which is the result. Now, what we're trying to show with this property is that if you switch the two numbers of the base and the result, you have to take the reciprocal of that to get them to equate each other. And while we have this property available, let's try and prove it. And the proof is actually quite quick and deceptively simple. So let's say we want to have some variables here to help us describe things a bit easier. What's going on? Okay, there you go. So let's say x equals log base b of a. And remember, a logarithm is the power to which you raise a base to get the result. So b to the power of x equals a. Then let y equal the log base a of b. And so what that means is a to the power of y equals b, because y is the power to which you raise a to b to get the result b. Now, because we have this expression here, if you look at this expression on top, if you see that we can prove x equals 1 over y, we're done, because we're just substituting in the variables. So if x equals 1 over y, we're done. And so let's see if we can get to that. Well, in this case, we have b to the x equals a and a to the y equals b. So why don't we just plug in this equation into this equation here? And so what you can do is substitute the b here for a to the y. And so you end up getting is a to the power of y to the power of x, I'll do it like this, is equal to a. Now that means, remember, that when you have an exponent raised to an exponent, it's the same thing as multiplying them together. So you have a to the xy equals a. And just so you know, this here is just a to the power of 1, because it's its own. Now, because these are the same base, you can notice that the exponents must be equal. So xy equals 1, and as a result, you get x equals 1 over y, which is exactly what we wanted to prove. So check, check, we're done. Remember, if x equals 1 over y, we're done. And we showed that because we just simply plug in the values of log base b of a and log base a of b. So that's really cool. That's really neat. We proved this property. So let's apply it to the problem now. And I'm just going to reproduce this expression below so that we can deal with it a bit easier without having to go back and forth. And so what does this mean? Now, if we apply the property to every individual term, we can see that the reciprocal is going to be log base 100 factorial, right, of 2. And because it's the reciprocal of a reciprocal, it's just flipped up to be a numerator with a denominator of 1, like this. We add that to the next term, which follows the same pattern. So log base 100 factorial of 3 plus ... plus log base 100 factorial of 100. Perfect. Now, this still looks pretty intimidating, but this is exactly where we introduce another property. Now, this logarithm property here is most likely not taught in schools anywhere because it doesn't seem to be very, very important, but is incredibly important because you're switching two bases. More likely, you've heard of the property that says log base c, and I'm just going to quickly write this, pre-write the colors, of course, again, because that will be faster in the end for us. So we get this. We get this, with the same base for the condition on which this property works is that the base has to be the same for all, which will be c. And so let's see, if we have the log base c of a times b, that's the same thing as taking the log base c of a and adding that to the log base c of b. That's our property number 2. I'm going to write that down. Property number 2. Now let's prove it, because that doesn't hurt. So once again, we're going to use the same tactic that we used to prove this property of using variables to sub in for complex expressions to try and get an easier way to work with these variables. So let's say let x equal log base c of a. Then we'll have let y equal log base c of b, and I encourage you to pause the video and prove this for yourself. It is not very difficult. Let z equal, guess what, right here, log base c of a times b. Now, with the same idea that we used for the first proof, we know that this is the power to which, x is the power to which you raise c to get a. So c to the x equals a. And then we can apply the same logic over here. C to the power of y equals b. And then c to the power of z is equal to a times b. Now we know that we have to prove that these are equal. So assuming they are equal, let's see what we can do. We can multiply the a and the b here to get ab, and we can multiply the c to the x and the c to the y. So let's say c to the x times c to the y equals ab, and we just multiplied these two equations together, right? Now what does that equal to? Well, we know that we have to make it equal to c to the z. Now let's find out if we can make that true. If we are assuming that these are equal right now, then c to the x times c to the y is equal to c to the z, right? And this looks like a not equal, but they are equal. We're assuming they are, so we're going to try and work with that. So we're assuming they're equal, so c to the x times c to the y is equal to the c to the z. And therefore, we can add these exponents together because we have the same base. So c to the x plus y equals c to the z. And because these are the same base, we have x plus y equals z. But guess what? We defined z as log base c of ab. We defined x as log base c of a. And we defined y as log base c of b. And we have x plus y equals z, which means that x plus y is equal to z. And therefore, we proved the problem. Wonderful. And now, we can use this powerful property, which is the one you most likely learned in school, and we can apply it in the problem below, right here. So what this means is we can use the reverse of that. We have the sum of the logs is equal to the log of the product. So they all have the same base, which is already good for us because we can see that this might work. right? The condition that we have met of being the same base c works here. And so what you end up seeing here is this becomes the same thing as log base 100 factorial of 2 times 3 times all the terms in between times 100. Now, if you know factorials, you should be getting excited about this, because let me just quickly recap what factorials do. N factorial is the same thing as n times n minus 1 times n minus 2 all the way to 2 times 1. What that means is that n factorial, and factorial in general, is a function that takes a number, usually in our case especially a natural number, and spits out the product of that natural number and all the natural numbers before it to 1. So for example, 5 factorial is equal to 5 times 4 times 3 times 2 times 1. That's equal to 120. And 3 factorial, for example, is equal to 3 times 2 times 1, which equals 6. And so we're going to use this idea here in this situation here. 2 times 3 times everything all the way to 100 is 100 factorial. But you might be thinking about this interesting situation here. What about the 1? Well, remember that multiplying by 1 is the same thing as doing nothing. So we might as well just add a 1 in this expression here, and then we get our actual definition of the factorial. And so we end up getting the beautiful expression here of log base 100 factorial of 100 factorial. This becomes this, using our knowledge on factorials. Now, remember, when the base and the result are the same, what number do you have to raise a base to get that same base? 1. And therefore the answer is just 1. And that's amazing to me. The fact that we took this whole scary, terrifying, complex expression, and using only 2 simple properties of logarithms that we were able to prove as well right on the spot, and fairly quickly at that, to get the beautiful answer of one of the most important numbers, 1. So this entire expression here, the sum of the 98 terms of n starting at 2 of 1 over log base n of 100 factorial is equal to a single number 1. And again, it's such a satisfying result because you just combined 3 terrifying concepts together and got a very simple solution using only 2 elementary principles of logarithms. And so you can go to your friends, you can go to other people you know, your math teacher even, and puzzle them with this OLYMPIAD problem and say, hey, can you solve this? I solved it in under 3 minutes. And if they say I have no idea, well, you puzzled them. Good job. But it's such a simple solution, and it's such a beautiful one as well. And that's why it's my favorite problem of all time. Now, there are others out there, and my question to you is, what is your favorite problem you've found out there? I'll see you in the next one.